So, having laid the foundation of BCS theory, that is how Cooper established that there could be a electron-electron attractive interaction mediated via phonons. Let us go over to start BCS theory. And before we start, let me tell that it involves some mathematics, that is algebra, which you should do because every step cannot be shown in the class. So, go through the steps yourself before you convince that the results that we are quoting are correct. So, postulate a many body ground state as this is a sum over. So, this is like psi 0 and this is all k greater than k f, and there is a g k, c k up dagger, c minus k down dagger acting on the 0. Here 0 is not vacuum, but it is the filled Fermi C. G k is some amplitude of the wave function, and C k up dagger, C minus k down daggers are two a pair is a pair created with momentum k and minus k with an up and down spins, and this is a many body wave function, a superconducting many body wave function, and then we have say m electrons, and we want to choose n of them to make n by 2 pairs, and the number of ways it can be done is m factorial divided by m minus n by 2 factorial and n by 2 factorial. For m equal to 10 to the power 23, this combination is equal to 10 to the power 20 to the power 20. So, in principle we have to solve for these many g k's in order to be able to write down a proper many body state, and which is an impossible task. What can be done is that one can treat the problem statistically, and in order to do that one can also take a grand canonical ensemble such that we do not keep the particle number fixed and instead talk about an average number of particles. So, we shall talk in grand canonical ensemble, and talk about average n, we call it as n bar instead of the number of particles. So, BCS ground state, BCS wrote down the ground state as a psi g, it is equal to a product of all these k 1, k 2 and k n, or say m, and this is u k plus v k, c k up dagger, c minus k down dagger, and acting on a phi 0. So, this is the field Fermi C as we have been talking about. So, the probability of a pair to exist, so a pair formed of k up and minus k down to exist is given by Vk square, and that this is unoccupied is given by Uk square. Let us write it as subscript. And of course, the normalization says that the Uk square plus Vk square should be equal to 1, which means that the probability that k up and minus k down would be either occupied or unoccupied, and the total probability is equal to 1. Take two states k 1 and k 2. So, the amplitude with uk 1, uk 2 represent no pairs in these two states. uk 1, vk 2, one pair k 2 and minus k 2, and vk 1, vk 2. Clearly distinguish your u's and v's. There are two pairs k 1 minus k 1 and k 2 minus k 2, both are occupied. So, these are the notations. So, a pair would be unoccupied with a probability uk mod square, and a pair would be occupied would be given by vk square, mod vk square. So, average number of particles n bar, this is equal to so the sum over k sigma and n k sigma, which is an operator, and this is equal to, we can write this as a psi g sum over k c k up dagger c k up, that is the number operator for up spin, and now we will have to also sum over spins. So, c k down dagger c k down, and this expectation has to be taken between the ground state that we have written here. So, that is the ground state postulate of the BCS ground state. So, we have to take this thing here, and this can be written as because there is no preference over one spin on another. So, we can simply write this as twice of psi g sum over k c k up dagger c k up and a psi g. This I am writing it once, but then later on I will skip. So, this will be a phi 0 u k star plus v k star c minus k down c k up, that is the psi g here, the bra psi g, and now I have a c k up dagger c k up, and now I have a u k plus a v k c k up dagger c minus k down dagger, and now I will have terms which are so this is the same case as it is there in the operator n k sigma, and now I will also have all the other terms in which k is not equal to or rather k is not equal to L, all the other indices which are not same. So, u L star plus a v L star c minus L down c L up, and now I will have a u L plus a v L c L up dagger c minus L down dagger, and there is a phi 0 here. Okay. So, this corresponds to k not equal to L, and the top one is for k equal to L. So, in principle u k and v k are complex quantities. So, let us write that u k and v k are generally complex. That is why the stars are written separately. And so, what we have done here is that we have used A phi psi as a phi A dagger psi. Okay. Now, look at the term L not equal to k. That is the term that is written later. Now, you can understand that this will have UL mod square, then UL star VL with a CL up dagger, C minus L down dagger, plus UL VL star and C minus L down, CL up, and plus a VL mod square C minus L down, CL up, CL up dagger, C minus L down dagger. Now, you can understand that so this is coming from the product of these terms, and so there are 4 terms which are here. Now, you can see that this term gives you 0 because it will create a pair, and so will change the occupancy of pairs in the ground state. So, it will have 0 expectation value. So, this term is not equal to 0, but then when you take it between this, then that is equal to 0. This is what I mean. And similarly, this term will also yield equal to 0 when taken between the filled Fermi sea. This simply adds a normalization, that it creates a pair and then it annihilates a pair. So, ultimately what happens is that, so L not equal to k gives you UL square plus a VL square equal to 1. And now, let us look at the L equal to k. This, if you look at it carefully, you will have a term which is a UK mod square CK up dagger C K up acting on phi 0 would give me 0, and UK VK, because this tells you that there are no states to annihilate for k greater than kf. And UK VK, the cross terms, both UK star VK and UK VK star will give 0 for the same reason as it is told above. So, the only term that contributes is the term with VK square. So, this n average, which is equal to twice of k VK square. So, that is the result. So, 2 comes because of the pair, and VK square is the probability of occupied states. Now, second thing is fluctuations in n bar. So, that is given by n minus n bar square, which is equal to n bar square, n square minus or minus twice of n bar plus a n bar square, which is equal to a n square bar minus a n bar square. So, this, if you again repeat the same calculation and use the same logic to cancel out terms, this is given by 4 k UK square VK square, and this is positive definite. In fact, V k as a function of k goes from 1 to 0, whereas U k as a function of k goes from 0 to 1. So, in a all happening in an energy range which is given by KTC. So, if you write down the variation of this, so this is my epsilon k or xi k, which is equal to epsilon k minus mu, and the V k drops from 0 to 1, and this is my superconducting gap delta. This is minus delta to plus delta, and this is my, so this thing is my minus h cross omega d to this as h cross omega d. So, in this range V k becomes from 1 to 0, and so the sum above goes as T over or T c over T f whole to the power n bar. So, this is the practically if you want to estimate the fluctuation in n. So, this goes as that. So, let us write down a BCS many body ground state. Or rather, let us write down a Hamiltonian. And the Hamiltonian is a single particle term epsilon k xi k sigma c k sigma dagger c k sigma plus a k l v k l c k up dagger c minus k down dagger c minus l down c l up. That is the Hamiltonian, and of course, we know that xi k equal to epsilon k minus mu. We have already argued that BCS theory cannot be obtained by doing a perturbation theory of any order. So, we will do a variational calculation instead. And the variational calculation with these small UK VKs, which are the occupancies, will be used as a variational parameter. So, what we have to do is that we have to take this variation and it is a k sigma xi k sigma n k sigma plus a k l a v k l c k up dagger c minus k down dagger c minus l down c l up. That is the, so we have to take a variation of this and put this equal to 0. So, let us look at the kinetic energy term or the single particle, the first term here. So, this is the kinetic energy and this is the potential energy. And this is given by, let us call this as kinetic energy operator, which is psi g sum over k sigma sigma n k sigma. This you should work out and get this thing as almost we have gotten this when we did the average number. This comes out to be 2 sum over k v k square and a xi k. And similarly, for the potential energy, we have V, this is equal to a psi g, and then there is a sum over K L, V K L, C K up dagger, C minus K down dagger, C minus L down, C L up, and this comes out to be K L, V K L, U K star, V L star, U L, V K. So, these are the kinetic energy and the potential energy, these are the expectation values of those, with of course, the constraint as U k square plus V k square equal to 1. Now, because of this constraint, one can actually take a pair and reduce. So, a pair of variables like this and reduce the number of variables from 2 to 1. See, it is always very difficult to do a variational calculation with two variational parameters, then you have to look for the minimum in a space, in a two dimensional space. It is much easier to look for a minimum in a one dimensional line, and that is now given by this single variable theta k. So, we can take u k equal to sin theta k and v k equal to cos theta k. You can take the other combination, that is u k equal to cos theta k and v k equal to sin theta k, but it seems that this combination works better. So, now what we do is that we take a variation with respect to theta k of this. Now, I will use a dummy variable k prime 1 plus cosine 2 theta k. Once again, this algebra you should do, because we have come from a v k square, which we have written as 1 plus cosine 2 theta k, and there is a k prime L. So, there is a v k prime L sine 2 theta k prime sine 2 theta L, and put this equal to 0 in order to do a variational calculation and see that what is the extremum value of theta k which minimizes the energy. So, minus 2 xi k sin 2 theta k after you do this derivative. So, it is L and there is a v k L cos 2 theta k sin 2 theta L equal to 0. If we define delta k equal to minus half of sum over L v k L sin 2 theta L, then using this and putting it into this equation, one gets a nice equation such as 2 xi k sin 2 theta k equal to sum over L v k L cos 2 theta k sin 2 theta L equal to minus 2 delta k cos 2 theta k. Thus, 2 xi k sin 2 theta k is equal to minus 2 delta k cos 2 theta k. Now, this equation gives as tan 2 theta k. If I divide or rather bring this below, it is equal to a minus delta k by xi k. So, this can also be written as sin 2 theta k cos 2 theta k, which is equal to minus delta k by xi k. Now, if we use the definitions, that 2 u k v k, which is equal to sin 2 theta k, this is equal to a delta k divided by a xi k squared plus a delta k square. So, this is my sin 2 theta k, definition of sin 2 theta k, which is also equal to twice of u k v k, and also v k square minus u k square, which is equal to cosine 2 theta k, which is equal to xi k divided by root over xi k square plus delta k square. There is a little bit of understanding that needs to be done here, is that this particular choice we could have taken the other choice also, that is a vice versa, but this choice fits all the definition, and we have taken the cos 2 theta k to be negative, because if xi k is large, which means that epsilon k is much greater than the chemical potential mu, then V k should go off to 0, which is apparent from this diagram. So, that is why the cosine 2 theta k is taken with a negative sign. Alternatively, we could have taken the sin 2 theta k, but that would not have satisfied the conditions or the boundary conditions that we have. So, hence the quantity delta k assumes a form that delta k equal to minus half of sum over L V k L sin 2 theta k, and hence this is equal to minus half sum over L V k L delta k divided by, putting the value of sin 2 theta k here, is delta L square plus xi L square. So, that is the definition of delta k. So, a trivial solution. So, we have to solve for these in order to solve for delta k. A priori, let us say that the delta k is really the energy gap or the superconducting energy gap, and we have to solve for it in order to find that what is the, or how does the gap vary with different parameters, especially say V and xi L, or how does that enter into the expression of the gap. In order to see that, we can also look at this expression and see that a trivial solution is delta equal to, rather this is delta equal to 0 is a trivial solution. Now, you see delta is there on both the sides of the equation. Here it is just a standalone delta k, and here it is sum over L delta L, and k is not equal to L. So, for a given momentum value L, delta L is a value, and delta k has to be computed by summing over all those delta L. But since we are solving for delta L, we do not know what it is. So, we cannot, so the unknown quantity appears on both the sides. So, a trivial solution, as we said, delta equal to 0. So, what does delta equal to 0 gives? It gives that 2 u k v k equal to 0, because you see that 2 u k v k equal to delta k. So, if delta k equal to 0, 2 u k v k equal to 0 from this equation. So, 2 u k v k equal to 0, and that tells that we also have a v k square minus u k square equal to minus 1. But then we have the normalization condition is that u k mod square plus v k mod square, it is equal to 1, that it tells that v k square equal to 0. So, a delta equal to 0 implies that v k square equal to 0. So, there are no pairs, and hence this should correspond to the normal state. So, the trivial solution is important because it talks about the normal state, but at the same time it gives a meaning to delta. Now, delta can be used as an order parameter for the superconducting transition, because at normal state delta is equal to 0, and delta is not equal to 0 for the superconducting state. So, now go to the original Cooper's proposition. That VKL equal to minus V if xi k minus xi L is less than h cross omega d. Thus, delta k equal to half V sum over L sin 2 theta L for psi k minus psi L is less than h cross omega d equal to 0 otherwise. So, this tells that as if delta does not depend upon k, it simply depends upon it is just a number. So, that is even more convenient because delta is now can be truly thought as a number which when is non-zero will give a superconducting state. However, when it is 0 it will give rise to a normal state. So, then we have delta L which has to be put here. Yeah. So, this says that if it is sum over all L, delta loses the k dependence. So, it is just a number and has no k dependence. So, we can write this as delta equal to V by 2 delta sum over L 1 divided by root over delta square plus xi L square, and we can cancel delta from both sides, and this gives rise to an equation which is a V by 2 L and a root over delta square plus. So, there is no delta L. So, it is equal to xi L square. Now, this is the equation for delta. You may not see delta on the left hand side to solve for, but there is delta in the right hand side and in the denominator and in the square root of a denominator. That tells that it is a highly nonlinear equation and you have to solve it either by a root finding method or one of the root finding methods such as Newton-Raphson or bisection method if you want to do it using a computer, that is numerically. We can also solve this problem analytically by converting this sum over L to an integral which is of this form. Remember, the V is the strength of the attractive potential. So, it is once when we convert a summation into an integral, we need to bring the density of states, or we can write down the density of states like this and do this integral such as, so there is a 2 and delta square plus xi square, where xi is the variable. Now, the integral will be from 0 to h cross omega d. This is what we have said earlier. Cooper had explained that how the pairs have to be formed within an energy shell of h cross omega d from the Fermi surface. So, it is measured from the Fermi surface, and now n of xi, the detailed feature of n of xi is not required because we know that this whole phenomena is occurring at the Fermi level. So, we can write this as n of epsilon f by 2 0 to h cross omega d d xi and a root over delta square plus xi square, and that tells us that this is equal to 2 by n v and this is 0 to h cross omega d d xi root over delta square plus xi square, and this is equal to 2 sine hyperbolic inverse xi by delta and from 0 to h cross omega d. If we put these values and rearrange, then we will get delta equal to h cross omega divided by sine hyperbolic 1 divided by n epsilon f v. Now, since we are talking about for weak coupling superconductors, n epsilon f v is much smaller than 1. Thus, delta assumes a form which is 2 h cross omega d exponential minus 1 by n e f of v. So, we are getting a similar expression for the energy gap as we have done by solving a 2 particle Schrodinger equation. This tells that this much of energy has to be supplied in order to break a pair and go from a superconductor to a normal state. And in BCS theory, this energy gap is a scale which is given by the temperature scale. So, delta is of the order of KTC, and so a KTC becomes equal to 1.14. It is actually 2 here as we have written there. And very accurate calculation shows that this is equal to 1.14, and so the TC expression is obtained from here. We will just do it in a minute. So, this gives the how the energy gap depends upon the phonon energy spectrum, and how the density of states at the Fermi level come into the picture, and the strength of the attractive interaction is also there, which is V, and we also have n epsilon f multiplied by V is much smaller than 1, which is relevant for a weak coupling superconductor. So, let us give you all these occupation probabilities, or what are also called as coherence factors, that we have a V k square equal to half of 1 minus psi k by E k, which is equal to half of 1 minus psi k divided by root over delta square plus psi k square. So, that is V k, and U k square is simply equal to 1 minus V k square, which is equal to half 1 plus psi k by k. So, these are important because these decide the behavior of the gap, the k dependence of the gap. Now, let us go to the finite temperatures. So, we have seen that let us write down the BCS Hamiltonian once more, which is a mean field BCS Hamiltonian. So, this is equal to psi k C k sigma dagger C k sigma, and in the mean field picture we have a minus delta k C k up dagger C minus k down dagger plus a delta k star C minus k down C k up. This would be obtained if you take the mean field decoupling of the PE term, of the potential energy term. These kind of decouplings we have done earlier, and this equation or rather this Hamiltonian can be diagonalized using a Bogoliubov-Valatin transformation where the C operators are transformed into quasi-particle operators of this form: C k up equal to U k star gamma k 0 plus a V k gamma k 1 and a C minus k down dagger equal to minus V k gamma k 0 plus U k gamma k 1. And so, gammas are quasi-particle operators so they have, so gamma, gamma dagger have usual anti-commutation relations. As the CK daggers. Now, a generic form of the gap, now we will call delta as the gap, because we have established that delta is non-zero for the superconducting state and 0 for the normal state. So, this is equal to a minus, you can call it L, and a VKL and a C minus L down C L up. So, a little bit of algebra in terms of this gamma operators will yield VKL U L or UK star Vk and 1 minus gamma L0 dagger gamma L0 minus gamma L1 dagger gamma L1, and this at finite temperature is given by each one of them will be given by a Fermi distribution function, which is or this is EL and EL. Thus, 1 minus gamma L0 dagger gamma L0 minus gamma L1 dagger gamma L1, it is equal to 1 minus twice of EL, so to say. So, delta k, putting it back into this equation, the gap equation, it is equal to minus VKL UL star UL. So, this should be L actually, UL star VL, UL star VL and 1 minus 2 FEL, and this is nothing but tan hyperbolic beta EL by 2. So, with VK prime equal to minus V, which is Cooper's assumption, I get this equation as 1 over V equal to half sum over k tan hyperbolic beta EK by 2 by EK, again converting that sum into the integral and using the density of states to have a value that is at the Fermi level. So, this is equal to a 1 in this and a 0 to beta CH cross omega C by 2 a tan hyperbolic x by x dx, where x equal to beta EK by 2. This integral as a standard value, which is given by log of 2 e to the power gamma by pi beta c h cross omega c, where beta c is equal to 1 over k T c and gamma is the Euler constant, which has a value 0.577, and hence this 2 e to the power gamma by pi has a value 1.13 or 14, around 14, and that if you simplify this, it comes out as k T c equal to 1.14 h cross omega c exponential minus 1 by n epsilon f v. This is exactly the formula for T c that we have got. So, this is the how T c varies with the phonon frequency and the density of states at the Fermi level and V. So, thus delta 0, so that is the value of the gap at t equal to 0, it is equal to 2 divided by 1.14, which is equal to 1.67 nearly, and that tells you that this is a feature of BCS superconductivity, that twice of delta divided by k T c it's equal to 3.52. This is followed by all weak coupling phonon mediated superconductors. Okay. So, this is a feature, or rather a property of this, that the twice of the energy gap versus divided by T c or k T c should be a number which is 3.52. It deviates strongly for the high temperature superconductors. So, let us summarize what we have seen so far. We have generically talked about the properties of superconductor. And those properties include the Meissner effect, that is the electromagnetic response, then the thermodynamic response, and the conducting properties, or rather the resistivity, how it suddenly drops to 0 below certain critical temperature or threshold temperature, and so on. And then we have gone on to talk about what is the origin of attractive interaction. And this tells explicitly that there is a phonon part involved, a role of phonon is very apparent because of the isotope effect that we have seen, because the Debye frequency actually scales as the ionic mass. So, the lattice is or rather the T c scales with the ionic mass. So, the involvement of the lattice is very clear, and there we can actually, for a narrow energy range, we can get an attractive interaction between the electrons. So, the wave function of the electrons will have to actually select this energy range to form a bound pair. And then we have written down a many body ground state and have taken a Hamiltonian, which is a generic Hamiltonian, where an interaction is taking place between two particles. For a particular form of this interaction term, that is V k k prime equal to a minus V for the epsilon xi k minus xi k prime to be falling in this energy interval h cross omega d, we find that the gap or rather we have been able to write down the equation of a gap, and also at finite temperatures have able to write down the temperature dependence, or rather the Tc, how the Tc, the threshold temperature, the critical temperature depends on these quantities such as V, that is the attractive interaction, the density of states, and the phonon frequency, call it omega d or omega c. So, this is in a nutshell what is superconductivity all about. And so, as you either destroy superconductivity by using temperature or thermal effects, or you destroy superconductivity by applying magnetic field, the state goes on to a normal state, a metallic state, which is apparently not the case for the high temperature superconductors, and they have many other complications. There are very little consensus whether phonons are involved into this pairing mechanism, or there is something else that is involved in any case. And also these behavior, or rather this 2 delta by KTC that we have found to be 3.52 is a value that is much higher, maybe 5, between 5 and 6, and which are not at all called as the weak coupling superconductors. And these high temperature superconductors, they belong to a class of non weak coupling, rather strong coupling superconductors.